refiners must be aware of crudes that are more prone to fouling. Specific crude properties and contaminants increase the likelihood of fouling. There are also certain practices and conditions that also lead to fouling. Shale crudes, which are inexpensive and can provide better margins, have high wax content that can form an asphaltenic sludge when mixed with heavier crudes. Also, amines used to reduce hydrogen sulfide content can cause both fouling and corrosion. As discussed in seminar number 3 on crude selection, some crude properties and contaminants are known to cause fouling in refineries, as shown in the table. These properties include asphaltene content, compatibility, paraffin content, sediment content, TEN or total acid number, and contaminants. Asphaltenes, which make up the most polar and aromatic fraction of crude, have been known to cause fouling when unstable. As discussed in video 5, soluble solutions colloidal dispersion solution model states that in stable crudes, asphaltenes are generally dispersed by resins, and later dissolved by small ring aromatics, then by saturates or paraffins. When this process occurs, asphaltene instability and subsequent fouling do not occur. The figure on the right shows the colloidal dispersion solution model. The resins in petroleum normally associate with the asphaltenes and act to peptize them. Key to oil stability is the ratio of resin to asphaltene. If the resin to asphaltene ratio is too low, not enough resins are present to peptize the asphaltenes and the molecules may precipitate out of the solution and present a fouling problem. Excess heat can break down the resin to asphaltene complex into a pre-coke species, which can occur in heat exchangers. This occurrence involves the polar, para-condensed asphaltenic species and may occur regardless of the compatibility of the crude blend. That is to say, suspended and soluble asphaltene constituents can become insoluble and foul heat transfer surfaces. However, the ability of resins to stabilize asphaltenes varies among crudes. Typically, heavy crudes with a higher resin to asphaltene ratio have less asphaltene instability issues compared to lighter crudes. While resins stabilize asphaltenes, the relationship between the two components is rather complex. Resins with strong self-interaction tend to cause asphaltene destabilization. Other components have been shown to influence asphaltene flocculation. According to one study, naphthenic acids delay the onset of asphaltene flocculation caused by the addition of N-heptane. High amounts of saturates or paraffins have been shown to encourage asphaltene precipitation. This occurrence, however, is dependent on the size or carbon number of the paraffins. Asphaltene instability is becoming an increasing concern due to strong interest in refining blends of paraffinic tight oils with asphaltenic dumbbell crudes. Because of this, asphaltene flocculation remains an active area of research. The blending of incompatible crudes to create a so-called dumbbell blend may lead to numerous problems in the refinery. These incompatible blends often cause asphaltene instability, which leads to fouling and processing difficulties that reduce the benefits of purchasing opportunity crudes. Asphaltene instability from incompatible crudes can cause extensive fouling in the crude preheat train. This will result in decreased energy efficiency, increased CO2 emissions, and increased frequency where heat exchangers need to be cleaned, and, in a worst-case scenario, reduced crude throughput leading to significant financial losses. As previously highlighted in video number 5, we are not compatible. Selecting compatible crudes is very important as fouling is a serious consequence from crude incompatibility. Light tight oil has significant levels of paraffinic hydrocarbons, which can undergo cracking to form polynuclear aromatics or PNAs and coke. It is reported that fouling rates can increase by 50 to 600% if the furnace outlet temperature rises 10 to 40 degrees Fahrenheit or 5.5 to 22.2 degrees Celsius. This causes problems such as the formation of sludges, solids, and waxes in crude storage tanks and lines, which include the lines utilized to transfer the crude out of tankage to the CDU. PNAs can also form from the wax of shale crudes. This negatively impacts overall refinery operation and profitability. The blending of paraffinic crudes with asphaltenic crudes promotes stable emulsions in the desalter and fouling in processing equipment. One crude high in paraffin content is waxy crude from Utah's Uinta Basin in the United States. Acidic crudes often contain calcium and other divalent metals in the form of naphthanates, which originate from the production water under conditions of alkaline pH. These naphthanates are soluble in organic media and thus can be carried downstream of production. In the refinery, they can precipitate, causing fouling issues such as desalter emulsion stabilization and fouling in the CDU preheat exchanger and heater tubes. When calcium naphthanates increase oil conductivity and decrease desalter voltage, this increases the fouling potential in the preheat train, which can lead to carryover of water into the atmospheric distillation unit. Certain contaminants in crude oils cause fouling in refinery equipment. Filterable solids, in particular organic solids and asphaltenes, contribute to heater fouling. As a general rule of thumb, 20 to 40 pounds of solids per barrel of oil or more will cause increased furnace fouling. The relationship between solids removal in the crude desalter and preheat train and furnace fouling was discussed at a past U.S.'s National Petroleum Refiner Association or NPRA Q&A session. The filterable solids content of the incoming feed should be monitored, especially when processing heavy opportunity crude, which are known to carry metals, clay, and iron oxides, to alert the refinery of potential upsets and allow the adjustment of desalter operations such as mix valve delta P and chemical treatment dosage. Asphaltene stability can also be screened for potential upsets. The liberal use of sodium hydroxide can also increase fouling. Nitrogen, which is usually at less than 0.1 weight% in crude and often concentrates in the heavier product fractions and residues, causes fouling in the main column overhead. Organic chlorides, which usually result from contamination from tankers, barges, dumping into pipelines, and refinery slops, cause fouling the crude tower. Scale inhibitors, emulsion breakers and other upstream additives containing phosphorus are causing problems. With respect to fracking fluids, those are limited to Western Canadian light fields where the geology is clay-based. In the lower 48 it is all carbonaceous for the most part and there are no phosphorus-based frac fluids being applied, yet there is severe consistent phosphorus fouling in some of the West Texas refineries according to Sam Lordo of Nalco Champion. Our previous seminars, What's in Your Crudes? Parts 1 and 2 covered common non-metal and metal contaminants and discussed analytical methods and commercial analyzers that could detect some of these contaminants. Studies at the Tulsa Joint Industry Project indicate that there is a direct correlation between fouling rates and the amount of metals. While light tight oil tend to have high metals content from fracking fluids, metals are also commonly found in both heavy and light crude oils in various amounts and are present either as inorganic salts, such as chlorides of sodium and magnesium, or as organometallic compounds, such as nickel and vanadium porphyrins. The table on the right displays average metal contents for crude samples of both Bakken and Eagle Ford shale formations in the U.S. In addition to crude characteristics, there are other reasons why crude fouling occurs. The practice of adding slops to the crudes being processed and the exposure of crudes to high skin temperatures or heat fluxes can lead to fouling problems. Increased light ends in the crude feed have a possibility of premature vaporization upstream of the desalter and the crude unit heaters. Higher vaporization can result in settling of solids on heat transfer surfaces. This can be prevented by the addition of an atmospheric pre-flash. While this practice can reduce pressure drop and prevent premature vaporization and fouling by asphaltenes in the crude unit heat exchangers, it can decrease overall unit yields as well. Here is our sponsor's experience. OCMS Seminar 1 discussed crude column fouling resulting from addition of phosphate esters during crude production that break down in the crude column. Crude column fouling can also occur from thermally unstable phosphate esters used as naphthenic acid corrosion inhibitors. The pictures shown are from a column that was using such a product. Any corrosion inhibitor containing phosphorus is subject to thermal degradation that can result in fouling. Tensient is a breakthrough in corrosion science that allows for safe and reliable refining of high-tan opportunity crudes. Reduced risk of phosphorus fouling and more effective passivation and ongoing corrosion protection can be achieved with up to 80% less phosphorus than competitor HTCI products. Tensient is different than any other commercial phosphate corrosion inhibitor. It is an ethoxylated triester with unprecedented oil solubility, thermal stability, and is non-acidic. Tensient reduces risk of phosphorus fouling and increases corrosion protection with up to 80% less phosphorus than competitor products. Tensient is making it easier for refiners to use more high-tan crudes.